Hello students. In this video, we're going to look at several math operations that apply to some different labs. This is not a procedural video about one particular lab. What I want you to gain from it is an understanding of how to manipulate equations in Excel, an understanding of the parameters of units and significant figures, and also what it means to verify a constant. In this case, we're going to verify gravity, the acceleration due to gravity on planet Earth. Okay, so here we go. An object that starts from rest and then accelerates at a constant rate of g. The distance it travels after time t is expressed as d equals 1/2 gt squared. Distance equals 1/2 times gravity times time squared. Okay? Typically, we're trying to verify the constant, and therefore we need this equation to equal g, because g is the constant. So I'm going to pause and show you a different picture to show you how to rearrange an equation. Okay, so here's the equation we were looking at in Excel, and this is what it looks like if you write it out by hand. Okay, distance equals 1/2 gravity times t squared. Okay, you need to isolate g. These are basic principles of math that you should have learned in middle school, but we don't practice them, so here is a review. In order to isolate g, you need to get all this other stuff away from g, and you need to apply things to this side to cancel these out, but anything you apply to this side of the equation has to be applied to this side. So the first thing is I'm going to get rid of t squared. How am I going to do that? I'm going to divide the whole thing by t squared, because this is really t squared over 1 divided by 1 over t squared. That cancels out, okay? But in order to do that, I need to also divide distance by time squared. So now we have 1/2 g equals d over t squared. How do we get rid of 1/2? Well, what times 1/2 equals 1? 2. Okay, there's an implied 1 in front of these alphabetical expressions in algebra. So 2 times 1/2 equals 1, cancels that out. Now I need to multiply this side by 2. The result is 2d over t squared equals g. This is the equation we're using, okay? It did this for you in the lab manual if you were looking at the data collection lab, and it's probably also there in the pendulum lab. But you need to understand how you go from point A to point B. Righto, so there it is that we were just talking about. Now, this is data submitted by a student when I was trying to figure out their math regarding the G constant. So in the data collection lab, for example, there's actually no G constant work to be done with this particular data collection. But we are going to use it in that way just to prove a point. I want to show you some things that are commonly wrong with student data sheets. Okay? Here, you cannot use math with the expression 2m. The units have to be up here, so it has to say distance equals meters, or distance parentheses meters. All right, now the seconds over here, that's fine. This all looks very obvious, except right here, this is not time divided by seconds. It's time seconds, okay? We're good, and then bam, we get this column that says miles per hour, but there are no columns in here that have anything to do with miles per hour. So how'd you do this? I can't really help you if you don't have the raw data going into this number. So let's look up here. So I added a column called distance in miles, and I added a column called times in hours, okay? And I actually asked Google, convert meters to miles. And I got this equation right here, or this constant right here, all right? So how am I going to convert this to miles? I'm going to say equals. I'm going to click over to here in this cell, okay? Oops, don't want to do it right now. And then there's my constant for the conversion factor. There you go, okay? But let me put this back to 20, and we'll talk about that in a second, because the data that the students gave me was 20 meters. All right. Now I did the same thing over here in times, okay? Time, hours. If you want to how many convert seconds to hours, here's your conversion factor, okay? Equals L6 times conversion factor. Done. Now you want to drag this equation through the entire column. You're going to click and hold at the bottom right corner of the cell and drag it down. And what does that do? It puts the same equation in each cell, but it uses the accompanying data from the nearby column. Okay? If, for example, you were going to put something in an equation and pull it down, but you were going to use a constant value, like the average of these measurements, then you would need to put a currency sign in here. L $6. Now look what happens. You drag it down, and L6 stays constant. Whereas before we actually want it to take L7 and L8 when we get to those rows. So I fixed it. Now over here, remember down here we just had a column with some numbers. There's no way to verify this. But now I have all the base numbers going into the calculation in my spreadsheet. So my instructor or my classmates can help me figure out where I went wrong, okay? And then I took the average speed right there. Notice that in many Excel equations, you use words to describe the operation. So for average, you actually say average. All right. Now that solves that. What did we just measure? That is the horizontal vector, okay? The horizontal distance when you throw a ball across the landscape, all right? But guess what? The horizontal vector is independent from the vertical vector. We now know the value for the horizontal vector, but guess what? We also know the value for the vertical vector because g has a constant. Does anyone remember what that constant is? G equals 9.8 meters per second squared, okay, or per second. We are trying to verify this constant, so I urge you in your mind to just memorize that the acceleration due to gravity on planet Earth is 10 meters per second squared, okay? I just rounded 9.8 up to 10 because that's an easier number to look at. All right, so here we have G. The first thing we did at the beginning of this video was figure out how to isolate G. Here's our equation. Now we need to put it back into Excel with D and T, which we have collected. So 2 times the distance, and the distance here is G6, okay, 20 meters, divided by L10, the average time in seconds. We want meters and seconds because we're working in the metric system, the SI system, in mathematics. Okay, raised to the 2IE squared. G equals 30 meters per second squared. Is that close to 10 meters per second squared? No, it is not. So as the instructor, I need to figure out what went wrong. Okay? So when I look at this equation here, all right, look, the time, it's what you measured. It was the response variable, the dependent variable. I can't really argue with that. That's the experiment. You use the stopwatch to derive these measurements, okay? Or to calculate them. They're not derived, pardon me. So I look at the equation and what other piece of the information could be wrong? Oh, okay. I'm looking for a factor that brings G equals 30 to G equals 10. So I'm looking for a factor that would change this by a factor of 3. All right. So I go over here and I think to myself, 20 meters. 20 meters is really far. It's pretty far. 20 meters is 60 feet. Okay. Not everyone can even throw a ball for 60 feet. I'm also thinking to myself, most people don't have meter tapes. They have measuring tapes that are in the English system. They have feet and inches. So what am I thinking? The first thought is that this is actually 20 feet and not 20 meters. How many meters are in 20 feet? Well, it's roughly 3 feet per meter. So if I tested my assumption that this potentially is the measurement that's wrong, I could say 20 divided by 3 is 7, roughly, okay? And now look at my G, 10.5. Is that close to 10 meters per second squared? Yes, it's much closer, okay? The next thing to do would be to calculate percent error, which I'm not going to do in this video, but essentially you verify how far away is 10.5 from 9.8, and that is your number is that percentage wrong or away from the expected value, which is 9.8 meters per second squared. The last thing I want to talk about is significant figures, okay? When you use Excel and you make an equation, oh, that wasn't a good example. I want something ugly. Let's get something ugly. Okay, here we go. I put 3.4 divided by 1.3, okay? How many significant figures here? Well, we have one integer before the decimal point and one after. Okay, we can't be more sure than this. But Excel gives us a return with 2.615385. We cannot be that sure. All of this noise, all of these numbers here to the left of the decimal, we just can't be that sure. This is a level of precision that we're not achieving when we start with numbers 3.4 and 1.3. So what do you need to do? You need to go over to home and you need to reduce these significant figures, okay? 8 is okay if it's one more significant figure than the numbers that went into it, okay? So that would be a correct number for this expression right here. Let's look over here. I already fixed all of this up before I started the video, but here we see a lot more numbers than what I just described. But let me just note quickly that zeros to the right of the decimal point are not significant. You need to get past the zeros. You have to get to integers other than 0, and then you can stop. So 0.00039 is correct, but this is not correct, and neither is this, because that doesn't mean anything. It doesn't give us any information. Now looking down here, we calculated G. Is this correct? No, it is not. We need to drop this down. There you go. All right, the last thing I'll say is this was the data provided by the students, and to do everything I just showed you, I didn't need this information. So bear in mind, keep in mind that you are working with the information that you need, not just all the information you measured and hoping that some of it is right. Okay, in this video, we learned how to use Excel, how to make clean and effective equations and tables in Excel, and we also verified the constant acceleration due to gravity equals 9.8 meters per second squared. We also verified our understanding that it doesn't matter if the ball is falling off the table or you're throwing it across the field. The horizontal and vertical vectors are independent. The acceleration due to gravity, no matter how the ball is put into motion, is always going to be 9.8 meters per second squared. Thanks.